In this video I will explain to you how to work problems using Galileo's law of falling bodies. To begin with, let's write down what our formulas were as discovered in the video that we watched. First, we had that the distance an object falls, or the displacement, is equal to 1/2 the acceleration due to gravity times the time squared. We also had that the velocity at the end of a given time period is equal to g times t, and that the acceleration is always the value of g, which is negative 9.8 meters per second here on Earth. So when we have a ball drop from a height, we know that the initial velocity is 0. The height is 17 meters. Now, if the height is 17 meters, let's just draw a picture of the scenario here. VI is 0, since it's just dropped. VF, I don't know. I don't know the time that it takes to fall. But I do know that the acceleration is equal to g, which is negative 9.8 meters per second, and I know that my displacement, since it's down, it's going to be a negative displacement of negative 17 meters. So, and I want to know how long it takes, in other words t, and I want to know how fast it's going just before impact, that is, the final velocity. So, if we use our free fall formulas there, I know d, I'm looking for t, so I can start with displacement is equal to 1/2 g t squared. I'm solving for t, so therefore I want to multiply by 2, and then I need to divide by g, and that's it. Take the square root, and that gives me t. So now I have solved my formula for the unknown variable, and I'm ready to substitute numbers and units. And so I have t is equal to the square root of twice the displacement, which was negative 17 meters, divided by the acceleration due to gravity, negative 9.8 meters per second. Now off to the side, if we look at our units, I have meters divided by meters per second squared, and that's all under a radical. So that becomes the square root of meters times second squared over meters. The meters cancel, and of course the square root of second squared is seconds, which is a good thing since I'm looking for t. Notice that I had a negative displacement, a negative acceleration, so it did give me a positive number under my radical, so it's not an imaginary answer. And you would put that in your calculator and do the arithmetic, and in the end you would want to round off to 2 significant figures. And I'll leave you the joy of actually putting it in there. So that's half the answer. The other answer is, how fast will it be going just before impact? Well, we're going to make use of this formula, v equals gt, in order to find that final velocity. G is negative 9.8 meters per second times whatever this answer is going to go in here. And so I get a negative answer, and you'll notice this time that this seconds cancels out that, and I'm left with meters per second, which is a good thing since I'm finding that impact velocity, or the speed just before or velocity just before it hits the ground. And again, you just multiply whatever your answer is here in the first step, and that will give you your value. And again, you want to round off to 2 significant figures. And that in general is how you do those problems. Next, if we again have a ball drop from a height, but this time instead of telling you the height, if I tell you the time it takes to reach the ground. So here I know what t is. If I wanted to find my displacement, displacement equals 1/2 g t squared. And this time I am solving for the displacement, so I don't have to solve for the unknown variable. It's already isolated. So this is 1/2 times negative 9.8 meters per second times 2.7 seconds squared. Notice how I wrote that. I put the 2.7 seconds in parentheses and the square outside. It's important that you notice that because this means that you square both the 2.7 and the seconds. And if you don't do it that way, it's not right. So be sure that you follow along. And when you're squaring a quantity, you put the number and the units in parentheses and your square on the outside. The reason that that's so important is here in my acceleration, I've got meters over seconds squared, if I wanted to write it in a simple form. And then I would have seconds squared, so that cancels out and leaves me meters. So you put that in your calculator. One of the main things students will mess up when they're doing these problems is they'll forget to square the time. So don't forget to do that when you use your calculator. And that will give you a certain number of meters, and it will be a negative number because of the negative acceleration due to gravity, and that would be your displacement. And since that's negative, that is going down. The question was from what height, so I wouldn't call it negative something for the height. I would just take the absolute value of what I get for my displacement. So I'm going to go ahead and put this one in my calculator since I have it handy here. 0.5 times negative 9.8 times 2.7 squared, and I get negative 35.7, and I'm going to round off to two significant figures, so my displacement is negative 36 meters for my displacement. But I would say that my height is 36 meters. You wouldn't say that you had a negative height. So that would be the height from which it was dropped. Now I want to know how fast it's traveling, so I'm looking for V equals GT, negative 9.8 meters per second times 2.7 seconds. Here, this second cancels this, and it leaves me meters per second for my answer, which is a good thing since I'm looking for velocity. My sign is negative, which indicates that it's going down, and certainly it would be going down if you dropped it. So I have negative 9.8 times 2.7, and I get 26.46, negative 26.46. Rounding for two significant figures would be negative 26 meters per second. And that would be what's called my impact velocity, the velocity just before it hits the ground. Alright, and then the final one in this set is a ball dropped from a height, and it tells you how fast it's going just before it hits the ground. You want to know what height it was released from and how long it was in the air. So if I know that V equals GT, and I want to find T, I would have to say T is equal to V divided by G. Now, the time that it's going down is going to be equal to the speed just before it hits the ground, and that would be in the negative direction, 26.9 meters per second, and G is negative 9.8 meters per second per second. Let's look at those units. Meters per second divided by meters per second squared. Invert and multiply. Meters cancels. This seconds cancels the square, and it leaves me seconds, and since I'm looking for time, that's a good thing. You'll notice that time is a negative over negative, which is positive. Time should never be negative. So my answer there is negative 26.9 divided by negative 9.8, and that is 2.744 seconds. And actually, because of the negative 9.8, because of this, that's two significant figures. So I'll only keep 2 and call it 2.7 seconds. Sometimes on a test I'll tell you to use 9.80 or 9.81 for the acceleration due to gravity, and the only difference in working the problems that way is you have to consider your number of significant figures. So that is my time. Now if I know my time, I can find my distance fallen, that is the height from which it fell. D is equal to 1/2 GT squared, and so D is equal to 1/2 times negative 9.8 meters per second times 2.7 seconds squared. Notice I get my displacement is a negative number. Second squares are going to cancel these out, and it's going to leave me meters as expected. And let's see, 0.5 times negative 9.8 times 2.7 squared is negative 36 meters, and that would be my displacement. And so the height, you wouldn't say it was a negative 36, you'd say the height was 36 meters. Okay, and that's about how you work that problem. As you can see, we've just been using the 3 formulas given in Galileo's video. These will only work when either air resistance is negligible, meaning it's so small that you can neglect it, or if it's falling in a vacuum. And the main thing to remember is the object has to be dropped, not thrown. So when it's dropped, you know that the initial velocity is 0. If the initial velocity is not 0, then you could not use these formulas as they're written. You would have to take into account whatever the initial velocity is, and I'll show you that on the following videos.